Okay. So yesterday we talked about early Acheulean in East Africa. Now we go to North Africa at Casablanca in Atlantic Morocco. Behind East Africa, early Acheulean sites have been discovered in South Africa. In South Africa, but their age is poorly known and largely comprised between 1.6 and 1 million years ago. And as for East Africa, North Africa is rich in Acheulean sites, well known since the end of the 19th century. Research expeditions have multiplied over the years and several lower Paleolithic sites were discovered, but most of them lack a stratigraphic context, mainly due to the Saharan belt in this part of the continent. So the tempo and the mode of the early Acheulean images and its subsequent development are poorly understood in this part of the African continent. The only North African sites in a stratigraphic context are in Maghreb, due to specific historical events and geological mechanisms. An early Acheulean in stratigraphic sites was identified in 2 sites at Tigenif near Mascara in Algeria, and one of the longest Acheulean archaeological sequences in Africa was discovered at Casablanca in Morocco. The construction works started at the dawn of the 20th century in the city of Casablanca, demanded the opening of large quarries, allowing the discovery of an exceptional geological, paleontological, and also archaeological heritage. The same thing happened in Algeria at Mascara when the Acheulean site of Tigenif was discovered. In the region of Casablanca, the development of quaternary littoral deposit is really exceptional, beginning 6 million years ago and spreading over the Pliocene and Pleistocene, with an extremely detailed registration of the global climatic cycles. In these pictures, you can see the system of longitudinal dune ridges parallel to the modern coast. These morphosedimentary units are composed of marine and aeolian calcarenites that have left a succession of paleo shorelines since the end of the Miocene in the interior part to the upper Pleistocene and Holocene near the coast. Since the beginning of the 20th century, this sequence attracted many researchers, and the first geological and archaeological models were built. In the 50s, Pierre Biberson conducted large systematic collections and excavations, and in 1961 he published a work on the Lower Paleolithic of Atlantic Morocco. He followed the methodological approach of boards in Europe. He established the fundamental characters of the ancient Paleolithic industries and proposed also a terminology to their definition and the descriptive criteria. He defined also the guidelines of the typological evolution of these industries to propose a synthesis that represented the reference for more than 20 years for the ancient prehistory in Atlantic Morocco. In this volume, Biberson identified 2 main cultures in the Lower Paleolithic: the Peb culture, which was divided in 2 stages, ancient and evolved, and the Acheulean, divided into ancient, middle, and evolved. Biberson built this cultural model on the basis of his geological scheme, which came into widespread use for the Maghreb. He defined several paleo shorelines and their relative age from the early to the late Pleistocene, and interpreted each shoreline as a distinct quaternary stage with local names. This quaternary geological framework established by Biberson was first revised by Stern in 1978. But in the same year, a joint Moroccan-France research program began in Casablanca area, first directed by Jean-Paul Reynal and Fatima Zora-Alaoui, and then by David Lefebvre and Abderrahim Mourib. This program allowed the stratigraphic reappraisal of the classical localities and the discovery of new sites. Based on previous geological researches and on new field works carried out since 1985, David Lefebvre, Jean-Paul Reynal, and Jean-Pierre Texier revised the chronostratigraphical framework of the quaternary littoral deposits of Casablanca region and proposed a new Casablanca stratigraphic scale. So they identified four formations from the late early to the late Pleistocene. Today we will talk about the Oulad Hamida formation, where the early Acheulean was discovered at Thomas Quarry 1. This quarry was firstly investigated by Biberson and known for its human remain of a Middle Pleistocene age. The Moroccan-French program re-examined this quarry in 1985 and discovered the presence in a stratigraphic context of a rich lithic assemblage, together with fauna, dated approximately to 1 million years. This early Acheulean is in unit L, which corresponds to the bed 2 of the member 1 of the Oulad Hamida formation. And this is a succession of 2-3 meters of limestone banks in a continental fluvial lacustrine hydrosystem with channels and a temporary water table, followed by Eolian sands. In this unit, the archaeology is limited to archaeostratigraphic subunits L1 at the base of the sequence and L5 at the top. The industry from L1 subunits is the topic of this presentation. Unit L have been surveyed and tested on about 1,000 square meters and systematically excavated in 2 main areas, one of 68 square meters and another of 75 square meters. The 2 excavated areas yielded around 4,000 remains coordinated in their 3 dimensions. Here in this section you see level L1 at the base and the level L5 at the top. Level L1 yielded 4,000 remains. And most part of the artifacts are of quartzite, and only 15% is on flint. Quartzite assemblage is devoted on large cutting tool production and small flaking. Flint assemblage focuses exclusively on small flaking. First of all, some words about raw materials. Several types of quartzite are available in the Casablanca region, both as primary sources, you see here the outcrop near the beach, and secondary sources. So in this picture you can see both the quartzite outcrop and the present beach, which contains quartzite of all sizes and morphology. The same quartzite outcrops were available during Pleistocene in this region, near the site, as demonstrated by this outcrop at Sidi Abderrahman Quarry, one of the most ancient known sites in the Casablanca region. And another outcrop has been recorded at Thomas Quarry 1, but successively destroyed by carrying works. Although primary sources were available, hominins mainly exploited cobbles. So they collected cobbles in beach deposit. In the archaeological deposits were recorded mainly ovoid cobbles with flat, planoconvex, and biconvex cross-section. The size distribution shows that pebbles are very frequent, but knappers usually selected the medium-sized cobbles for small flaking and large cobbles for large cutting tools. It's interesting to note that large cobbles are very, very few. Besides, these cobbles are mainly rounded and occasionally present angles among surfaces that could facilitate the initial production. Medium-sized cobbles were exploited throughout several flaking methods, a panoply similar to that of the earliest African Acheulean. Now we will explore in detail these methods because the quartzite technology of this site has not yet published. We hope to do this the first month of the next year, so I would like to show you into detail the technical systems. Many cobbles present simple flaking. So they present a low count of removal scars with a random distribution. And in many cases, a longitudinal fracture is produced during flaking, breaking the core. This fracture spreads where the lines of weakness of the raw material are. Plano-convex cobbles, as in this case, have been used as a streaking platform and the convex surface as a flaking surface. Usually the first flake series show a sharper angle than the last series. Since the angle varies during the reduction sequence, it's very likely that the number of produced flakes is much higher than the negative on the core, as experimentation has also shown. When these cores are exploited, they are similar to the cores that in French are called galets tronqués. It means truncated cobbles. But there is no bipolar technique documented. All quartzite knapping has been performed using handheld percussion. Sorry. Okay. A flaking system, we have also a unidirectional exploitation from a rectified streaking platforms, both on medium-sized cobble, but in few cases, on pebbles. Another flaking system is the system known as SSDA. It means a system of alternate surfaces. The flaking is accomplished through a continuous rotation of the core. The first streaking platform is a natural surface of the cobble, and after each flaked surface becomes a streaking platform for the adjacent phase. Knappers obtained not more than 1 to 2 series of 4 to 7 flakes for each flaked surface, and a small number of hinged negative scars are visible. For this, knappers used usually angular cobbles, and the rotation of the core is conducted respecting the original orthogonal angles among the faces. We have also a multi-facial, multi-directional exploitation, and these are the most frequent cores. Core surfaces were alternatively flaked through multi-directional removals without a clear organization of the process. No specific platform preparation was conducted insofar as each negative serves as a strict platform for the following removal on a second phase. The cores in this category are typically small and overexploited. Some cores present a mature flaked surface with unidirectional long flake scars exploited at the beginning of the reduction process, and multidirectional removals on the other phases that correspond to the final core reduction phase. At this point, the main flaking surface was not most likely no longer functional, and some core testified the respect of an orthogonal shape during flaking. Another flaking method is the bifacial partial alternately, mostly on flat or slightly biconvex cobbles. This exploitation method shows unidirectional removals on two adjacent surfaces, and each negative scar is used alternatively as a streaking platform to flake the adjacent plane. It's interesting to note that regardless of the cobble thickness, the angle between the two surfaces is systematically between 45 and 54 degrees and could suggest the intention to configure a cutting edge. There is also discoid technology that is not so frequent among flaking methods. Knappers exploited biconvex cobbles, managing the peripheral convexity to respect the requirements of the discoid concept. This is for small flaking. Now, the large cutting tool production that is characterized by a large variety of tools. This picture shows the most frequent large cutting tools. Large cobbles with biconvex or plano-convex cross-sections were shaped through two series of non-invasive removals. The first phase usually corresponds to the point shaping. While lateral edges show a large angle variability, the angle of the point is more standardized and varies between 31 and 36 degrees. Its variation is not linked to the thickness variation of the blank, and no final retouch intervenes to delineate edges. This procedure suggests that the functional part of this object is the point, and that the angles has to respect a standard value. The same procedure has been identified in other large cutting tools. The only difference is the apical part. And in this case, the point is skewed, déjeté, by one or two large notches. Also, these tools show the same process, but in this case, the apical part corresponds to a transversal edge obtained through a final retouch. Flat cobbles were also used to shape peaks with very, very few removals. The point can be on the longitudinal axis or skewed, but the angle value of the point cutting edge is rather standard. In some cases, knappers used also entam large flakes with a triangular section. Pointed large tools can be shaped not only on cobbles, but also on large entam flakes. Shaping is limited on one face or to the marginal retouch of the lateral edges to create a convergence and thus a point. Here you can see the blow direction of the end-time flake, and usually the blow direction is located on the proximal lateral part of the large flakes. Large end-time flakes were also used as blanks for cleavers. The transversal cutting edge is obtained through the flaking, and the lateral edges are slightly retouched. In this case, the blow direction produce a side strike flakes. So it's possibly these flakes are produced anticipating the technical objective. It means anticipating the objective to produce a pointed index or a cleaver. The systematic production of entame flakes as large cutting tool blanks has been identified also by Gon and Sharon at Ternifine. The site of Ternifine has two names, Tigenif or Ternifine. The cobble opening flake core method produces a blank that was perfectly suited to index production, with a minimal necessity of secondary retouch. This method was highly controlled due to the meticulous attention paid both to raw material cobble size and shape selection, and to the systematic removal of a single pre-planed entame flakes. Here, you can see the entame flakes for Ternifine at the top, and entame flakes from Thomas Quarry 1, Untitled 1 on the bottom. At Tigenif, a second step of this method is also documented. Combewa flakes were detached in the second stage of manufacture after an entame flake had initially been removed from a flat cobble core. At Thomas Quarry 1, only one Combewa flake is present. This is casual, and a Combewa strategy is not documented at all. Another type of large cutting tool shows trihedral sections. The blanks can be cobbles in the bottom of these figures, and the split cobbles with the trihedral sections, or large core edge flakes belonging to the flaking of a large blocks. And to flake large blocks required the provisioning to large boulders. Large boulders are not so frequent in beach cobbles, so probably there is a possibility that some of these large flakes belong to the flaking of large boulders at the primary source. But we know that at Thomas Quarry 1 there was a primary source in the cave, in the quarry. In the L1 quartzite assemblage were identified also cobbles with percussion marks. The percussion marks are systematically located on the most protruding parts of the cobbles, usually at the extremities of the long axis. And most of these armstones were reused as core blanks. Here you see the cores with impact marks at the extremities, and here large cutting tools with impact marks at the cobble extremity. So now I would like to resume the main techno-cognitive components of the quartzite productions. Small flaking is based on a local provisioning system. Nappers used as core blanks, medium-sized cobbles available in cobble beaches. Core analysis document a panoply of debitage method that has been identified also in the East African late Old One and early Acheulean techno-complexes. Variation of flaking methods is linked to the geometry of the blank. Each flaking method corresponds to the best solution in exploiting a specific cobble shape. This means that nappers were able to anticipate the technical process, recognizing the geometric characteristics of the cobble and adapting the flaking method. The convexity management of discoid cores and the maintenance of orthogonal planes in the multifacial exploitations allowed a high level of flake productivity. These flakes do not show specific features, except in the case of the unifacial unidirectional exploitation on elongated cobbles that allowed the production of elongated flakes. Most part of the large cutting tools are on large cobbles, collected in the cobble beaches. Knappers were able also to produce flakes with specific features, as entamel flakes, and edge core flakes as blanks for large peaks. In other words, they were able to anticipate the final object selecting or producing the most appropriate forms. Bifaces sensu stricto are absent, cleavers are very few, and shaping do not involve the volume, but only the edges of the object. The main objective was to produce large pointed tools. This is for quartzite. Now we talk about, okay. Okay. The flint component of the seam assemblage revealed a particular process never encountered in the African Acheulean that we recently published on Scientific Reports. Knappers used flint pebbles with a maximum length of 6 centimeters to produce flakes. Flint outcrops in the internal phosphatic plateau of the meseta and was collected as pebbles from beach deposits in secondary position on the Pleistocene paleo shores. Here you can have a look of the flint outcrops and of the beach deposits. Half of the small cores show flaking methods performed by handheld percussion technique, similar to those identified in quartzite assemblage as unifacial unidirectional with the rectified sticking platform, the bifacial partial, and the multifacial multidirectional. But the other half of the cores display a bipolar technique on anvil and 2 different strategies. The bipolar longitudinal exploitation, which simultaneously yielded 2 flakes generated along the longitudinal axis from the pebble extremity in contact with the anvil. This extremity shows the percussion impact damages produced by the hammerstone's action. This method is well known in early technologies, and not only in early technologies. But another set of 32 cores is devoted to the production of bladelet-like flakes and shows a specific process, the bipolar on anvil semi-peripheral exploitation, independent from the other flint flaking methods and totally absent in quartzite flaking. These cores show 1 horizontal or a slightly oblique split surface along the transversal axis of the pebble and percussion marks on the opposite side. The semi-peripheral flaking surface displays several negative of bladelet-like flakes whose impact point generated from the split surface. In order to understand the role of the pebble split surface and the impact damages and the core positioning on the anvil, we performed experimentation. I hope that video, okay. So you see my colleague Abderrahim Moib, the co-director, the Moroccan co-director of the mission. And we selected a biconvex flint pebble, a quartzite hammerstone, and a large cobble as an anvil. First of all, he split along the transversal axis of the pebble, and he obtains an oblique fracture. Usually, split fractures or surfaces opened by a removal are used as streaking platform. But we couldn't produce flakes because the blank was not stable on the anvil. So we turned the half pebble and we strike on the cortex, and flaking the periphery of the pebble with detached elongated flakes. So here Abderrahim changed hammerstones and he strike on the cortex, and look the impact point in contact with the anvil. So this is the first flake produced. And here you can see the operational scheme and the results of our experimentation. So the quartzite hammerstone, the large cobble used as anvil, the flint pebble, the split transversal fracture or slight oblique, the rotation of the half split pebble, the positioning of the half pebble on the anvil, and the bipolar semi-peripheral flaking to obtain these very small bladlet-like flakes. Okay, and these are the bladlet-like flakes. It means elongated flakes with a length to width ratio approximately of 2. And their dimensions are well separated to the other flakes belonging to different exploitation, but also to the other bipolar exploitation. Since the old one, bipolar on anvil technique is known in lit productions, but it does not show a specific technical process. Bipolar semi-peripheral exploitation is a specific technical process addressed to a bladlet-like production. This process is made possible by the application of the concept of anticipation in the choice of the blank. It means choosing an elongated cobble with a long peripheral convexity, and thanks to a preliminary rectification of the pebble surface resting on the anvil to ensure core stability during reduction. Bipolar semi-peripheral exploitation is not regulated by the concept of predetermination, just by the concept of anticipation. This production demonstrates that the African Acheulean techno-economic strategies were much more flexible and diversified than the mere production of macro tools can document. It's clear that these bladlet-like flakes are not bladlet sensu upper Paleolithic. There are no standardization with the parallel edges. There is no predetermination of their morphology, but just to their length. So in summary, some conclusions on this early North African Acheulean. We don't know about local origin of this Acheulean because all the archaeological sites in Morocco are absent. Until now, despite almost a century of archaeological excavations, no Old sites have been identified in Morocco. The revision of lithic assemblages classified as by Biberson as Moroccan pebble culture are actually geofacts or younger reworked assemblages. We know that all the sites are in Algeria, in the Ain Anesh formation, dated between 2.4 and 1.7 million years. but these indices are separated by the early Acheulean by 700,000 years. This means that we cannot discuss about the local origin of this Acheulean. So we see if there are similar technological traits with the East African Acheuleans. First of all, this industry shows the large variation of the small debitage methods of the early East African Acheulean. What about large cutting tools? Contrary to the very early Acheulean, dated to 1.7, 1.6 million years in East Africa, large cutting tools at 1.4, 1.3 million years are repeated on a certain number of specimens that all tend towards same morphological aspects and produce several large cutting tool types. This happened both in East Africa and at Thomas Quarry 1 Unitel. Among them, these large cutting tools, pointed hand axes and picks are the most common types. Large cutting tool morphologies are planned through standard procedures in both production and selection of large cutting tool blanks and shaping. And the chain opératoire were never very long. When large cutting tool blanks are large flakes, specific flaking methods produce side strike flakes whose morphology anticipate the ultimate shape for large cutting tools. When large cutting tool blanks are cobbles or slabs, their natural morphology is selected as the most proper form to shape a specific tool type. This blending of blank procurement and production and the shaping process produce technologically and morphologically similar large cutting tools, and seems to represent a common background for the Acheulean technology dated to 1.4, 1.3 million years, both in East Africa and at Thomas Quarry 1 Unit L. The technical innovations recorded in East Africa since 1 million years are not present in the early Acheulean of Casablanca. There is no systematic provisioning to the primary sources, no concept of predetermination in large cutting tool blank production. Combewa method is widely used in East Africa since 1 million years. It is present at Ternifine in Algeria, but not at Unit L. There are no bifaces. Small debitage method variation does not decrease, and there is no emancipological and geometrical constraints of raw materials in small debitage. This means that if the early Acheulean spreads from East Africa, this dispersal should be earlier than 1 million years. But for the instance, this is just an hypothesis. Currently, new stratigraphic analyses were performed at Thomas Quarry 1, in particular magnetostratigraphy, and we are waiting for results. Finally, I would like to talk about a project concerning percussion for napping in this early Acheulean. This is a work in progress, and I show you just the preliminary results. We conducted this project with Amélie Bardot, a biological anthropologist and primatologist working on the evolution of tool use and manipulation in primates, and she works at the University of Kent in UK. This early Acheulean assemblage yielded a large quantity of hammerstones, entire cobbles used as hammerstones and hammerstones reused for artifact napping. In the early technologies, two categories of active hammerstones have been identified. The first one regroups the hammerstones with the fracture angles, used for activities other than napping, such as food processing. The use of these hammerstones is documented also in non-human primates. The second category regroups the active hammerstones used for napping, that display areas with highly concentrated pitting. In Old One and early Acheulean assemblages, these hammerstones, in East Africa, these hammerstones usually show the impact damages on the protruding parts of the cobbles. In these techno-complexes, the number of hammerstones is very low when compared to the napped objects. This is mainly due to the difficulty to recognize indisputable percussion marks, above all in a usually disturbed context. This is also due to a methodological bias, because the recording and analysis of the natural material from excavations is not always systematic. Besides, napping techniques in the early technologies have been identified thanks to experimental researches. Unfortunately, this approach usually lacks a strict comparison with archaeological data. More attention has been paid to the napped artifacts and scarce attention to the percussion gestures, both in technical and motor skill perspective, especially because the location of the impact damages on a cobble has not been analyzed. This lack of data has a huge implication on our knowledge of the hominin manipulative abilities. Only hominins are able to voluntarily make stone tools with a sharp edge. This is because they have great cognitive abilities and specific anatomical feature of the hand. To better understand the evolution of human manipulative abilities, we can look at the anatomy of fossil hands when available, but we can infer it by looking at the archaeological lithics and reproduce the technical processes. So far, this aspect has been investigated through the analysis of the napped artifacts, and only few cases through the analysis of the hammerstones. Our work focused on the handheld percussion in the early Acheulean of Casablanca. I would like to remember that hominins used the handheld percussion with a harder hammer to produce quartzite artifacts. No technical aspects of the bipolar napping have been identified in quartzite napping, but only in flint napping. In the case of flint, the quantity and quality of impact damages on the quartzite stones can be only due to the percussion of quartzite to quartzite, because experimentation demonstrates that the impacts due to flint percussion are very marginal and not so deeper as the impact due to quartzite percussion. So Unit L yielded 30 entire cobbles with pitted area, evidently used as active hammerstone for quartzite napping, and 84 artifacts showing pitted areas on the cortex remaining zones. The percussion marks are systematically located on the most protruding parts of the cobbles, usually at the extremity of the long axis. In previous years, we made experimentation to better understand the napping methods. The experimental hammerstone displayed percussion marks on the cobble edges and not on the extremity as for archaeological hammerstones, because experimenters used the handheld percussion with a tangential gesture. Our hypothesis is that the location and extension of these impact damages on the cobble extremities demonstrate the use of an orthogonal gesture in the handheld percussion. To test this hypothesis and to evaluate the archaeological and the paleoanthropological implications of the use of an orthogonal versus tangential gesture, we made a new systematic experimentation involving 3 experienced nappers with a good knowledge of the early Acheulean of Casablanca and with 10 to 30 years of experience in napping experimentation. Each napper performed 2 technical objectives, each one with both gestures. The 2 technical objectives correspond to the main productions identified in the archaeological assemblage, that is, the production of small, medium-sized flakes through a unifacial, unidirectional exploitation from a cortical streaking platform, and the manufacture of a pointed hand-axe cobble. The first question to be addressed is, were the hammerstone selection and the grasping patterns forced by manual constraints and/or by technical choices? The first step was to choose the experimental hammerstones accordingly with the archaeological evidence. I would like to underline that our knowledge of the selection modalities operated by prehistoric nappers is based on the analysis of the hammerstones and of all the cobbles and the pebbles without anthropic modifications from the excavated assemblage. So we selected for experimentation cobbles with similarly raw material, morphology, and dimensions to the archaeological ones. That to say, cobbles of a light gray quartzite, very well crystallized and slightly porous. We selected cobbles with ovoid volumes, subcircular and subtriangular shapes, and biconvex and planoconvex cross-section, similar to those of the archaeological hammerstones. The same for cobble dimensions. All archaeological hammerstones are on medium-sized cobbles. However, the presence of percussion marks on the cortical surface of the cobbles used as hand axes, blanks, also documents the use of large cobbles. For this reason, we have also selected the large cobbles as experimental hammerstones. Considering the grasping patterns, we measured the size of the hand and grip force of each experimenter as functional parameters. We analyzed the videos of each experiment by noting different behaviors such as grasping posture, orientation of the arm, movements of the arm, and blank placement. The second question concerns the hominin motor habits, if they allowed a repetitive streaking precision. During experiment, we counted the number of strikes to detach a flake, to quantify flake productivity and strike overlapping. To quantify the location and extensions of the pitted areas, we used 3D analysis of the archaeological and experimental hammerstones. The 3D models were obtained using photogrammetry, and we take photos of the experimental hammerstones every 5 strikes to analyze their lifetime and consequently the lifetime of the archaeological hammerstones. The last question concerns the technical products. Did the hominins adopt an orthogonal gesture to produce artifacts with specific feature? To answer this question, we recorded the number and type of technical accident and the flake dimensions and the flake platform dimensions in both archaeological and experimental series. Besides, we performed 3D photogrammetry of some experimental and archaeological flakes to process morphometrical analysis of the butt and the bulb of the flakes. We find specific patterns of grasping posture. The extended 3-jaw chunk grip for the orthogonal technique and the cradle 5-jaw grip for the tangential technique. Only one experimenter changed his grasping during experiment. The extended tree-jaw chunk involves more precision, and the hammerstone portion that impacts the blank is less extended than in the tangential percussion. Besides, the jaw chuck grip matches better the morphology of the archaeological hammerstones, while the cradle 5-jaw grip is more suitable for the use of elongated hammerstones. 3D analysis of the pitting areas confirms that the impact damages are located on the cobble extremity for the orthogonal technique, while the pitting areas are located on the side of the hammerstones for the tangential technique. Moreover, the percussion marks are much more concentrated in the case of the orthogonal technique and also show a greater dip in a given point. This means that repetition of orthogonal percussion shows greater precision than the tangential percussion. Here is an example of the lifetime of an experimental hammerstone used for orthogonal technique. You can see clearly the pitting area after 5 strikes, but with a clear dip and expanded area after 15 strikes. Nevertheless, we record some noise due to the use of photogrammetry method, and this is a limiting factor for this study. So Améline Bardot with other colleagues is experimenting another 3D method to elaborate this data. Previous studies used the hotspot analysis on ArcGIS to quantify the depth and perimeter of the pitting areas. This can be highly time-consuming when studying a larger sample. We currently develop a new method using morphological analysis on the free software, and this will be more rapid. We'll be able to get the detailed morphology of the pitting areas and escape the noise previously shown. Clearly, the minimum depth of the pitting areas is the same for both archaeological and experimental hammerstones. Regarding question 3, it means flaking products. First of all, we compare the flake productivity of each experiment. There is not a great difference between the two techniques, and the choice of the blank in terms of raw material and angle management has more importance than the technique. Some observation for the Syria accident that account for 80% in archaeological flake assemblages. Besides, the number of broken flakes produced during experimentation is low. The high frequency of archaeological broken flakes could depend more on the use than fracturing during the technical process. If we compare flake dimensions of the two experimental techniques with the archaeological ones, we observe that length and width distributions fall within the distribution of archaeological flakes for both techniques. The difference concerns the thickness. The flakes produced with the tangential technique are on average thinner than those produced with orthogonal percussion. The distribution of the thickness value of the flakes produced with the orthogonal percussion is wider and in agreement with that of the archaeological flakes. This also shows that hominins did not intend to produce particularly thin flakes. The same observation is made for the dimensions of the flake platforms, which are thinner in the case of the tangential percussion. In summary, preliminary conclusion of this work suggests that the adoption of an orthogonal handheld percussion with the hard hammerstones in the early Acheulean of Casablanca was due to the need to strike with repetitive precision. Consequently, knappers operated a strict selection of the cobble morphology for three-jaw chuck grasping. Thus, the use of this kind of percussion was not linked either to manual constraints or to specific productions. The tangential handheld percussion with the hard hammerstone was not used. Besides, the morphology of the archaeological cobbles used as hammerstones is not ideal for this type of percussion gesture. What does it mean in terms of evolution of hominin manipulative abilities? During the supposed period of the apparition of stone tool making, numerous hominin species living contemporaneously. Based on hand morphology, all of these species could be potential stone tool users and makers. Already with Australopithecus afarensis, we begin to see features considered as related to stone tool use and the grasping posture, identified both in the orthogonal and tangential percussion. That's to say, the extended three-jaw chuck grip and the cradle five-jaw grip. This may suggest that different hominins were able to use handheld percussion with the hard hammerstones, with both orthogonal and tangential gesture. However, the archaeological hammerstones documents a preference for three-jaw chuck grip. This could be due to several factors: the need to a repetitive precision, an ancestral behavior linked to percussion activities for food processing, or to the lack of suitable cobble morphology for cradle five-jaw grip. As I said to you at the beginning to this communication, unfortunately, the analysis of the unmodified cobbles from excavation and from the Paleolithic species is not available in most of the lithic studies. We must stress that before 1 million years, archaeological evidence suggests the exclusive use of hard stone hammerstones for knapping. Experimental studies demonstrated the use of soft hammerstones at 1 million years in East Africa. In the case of experimental soft hammerstones, the percussion gesture is always tangential, but the grasping posture is the power squeezy grip that require a particular morphology of the radial bones of the wrist. This posture is very limited for hominins before Homo habilis or before Homo erectus, as archaeological evidence suggests. With the tangential percussion, the thickness is the only different flake technical trait. This percussion produces thinner flakes, which are one of the patterns linked to hand-axe refinement, most related to the use of soft hammerstones, whose grasping posture is not documented before Homo erectus or maybe Homo habilis. One of the questions to explore in further analysis is if the tangential percussion is related to the use of a soft hammerstone for a specific technical production. And also there is a methodological problem. The discovery of very thin flakes related to a large cutting tool production is usually related to the use of a soft hammerstone. But is this right? It means it can be due to the use of a tangential percussion with a hard hammer. This is also a topic to investigate. In any case, at Thomas Quarry 1, Unit L, we don't have any trace of evidence for the use of soft hammerstones. And this is another aspect suggesting that this early Acheulean of Casablanca is earlier than 1 million years. but for this we are waiting for new dates and new chronostatic data. Thank you very much.